Okay, here we are, section 7.2, similar polygons. In all honesty, this is my second try at this one because the last one was way too long. So I tried to pare it down as much as I could to get just the bare essentials, and I'll probably move kind of fast, but there really isn't a lot that you're going to have to do other than write, a few things out and just take some time to go through the examples. So 7.2, similar polygons. We've talked about proportional, and that's basically all similar means is just proportional. So we've used proportions to solve problems. We have used now we're going to use proportions to solve similar polygons and solve problems using properties of similar polygons. We'll really do that more in class. So here we go. First thing is to define similar polygons. And really what I want you to understand is two parts to this. And you have to know this for your test. You have to know this for your quiz. Two polygons are similar if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. That's the key to similarity. Is the corresponding angles are congruent, corresponding side lengths are proportional. When we did congruent polygons earlier on in the year, corresponding angles were congruent and corresponding sides were congruent. So this is a little different now. And basically what's going to happen is, for the most part, every problem is going to consist of you setting up proportional segments. So like for this problem right here, we're going to do one just like this in a moment. They've given us two similar polygons. We know A is congruent to W, B is congruent to X, C is congruent to Y, D is congruent to Z. They've given us four pairs of congruent angles. So we've satisfied the first condition. The second condition is showing that the sides are proportional. So we do the corresponding sides, 15 to 5, 12 to 4, 21 to 7, 18 to 6. And they've done them over here for us, and these are a ratio of 3 to 1 for all of them. Now, the last part of this and this is called, showing corresponding angles. This is called down here actually the statement of proportionality sometimes, or the ratios of the sides. The last part here that's maybe new for you is how to say two polygons are similar. And what it actually is it's the exact same thing as congruent. We just don't have the equal sign there. So it's you notice the congruent symbol has the equal. This guy doesn't. So that's what similar means. So congruent has the little equal little curve over it. This one doesn't. Now, first problem here. In the diagram, the one you've got in your book, or when you've got in your notes, okay, it says list all pairs of congruent angles and write a proportion that relates the corresponding sides. You can do this from the drawing, try to match things up, but really the statement right here gives us everything we need to know. I know that angle N is congruent to angle U because they're similar. Angle P is congruent to angle V. Angle Q is congruent to angle S. And angle R is congruent to angle T. So I've already got my angles marked up there. So angles, angle N congruent to angle U. Angle P congruent to angle Q. Angle, dang it, not Q, angle V. Angle Q is congruent to angle S, and angle R is congruent to angle T. Just try to keep you on your toes there by making a mistake. Now the statement, write a proportion that relates the corresponding sides, that's sometimes again called the statement of proportionality. Basically, again, use the statement. I'm going to say NP corresponds to UV, which you can see NP, UV, those guys correspond here. So NP over UV. Now once I do that, that means this guy has to be first, this guy has to be second. So once I did NP to UV, I'm going to do PQ to VS. Then I'm going to do QR to ST. And NR to UT. There we go. All right, so there's my statement. Now, the next problem then is scale factor. We're going to come back to scale factor later on in the year because of the fact that later on in the chapter, because we're going to talk about dilations and stuff like that. So we will need scale factor, but for right now, the book kind of is iffy about it. The definition is the ratio of the two corresponding lengths of sides. So ratio of the lengths of the corresponding sides of two similar polygons. That's the definition of scale factor. Now for this one, and this is important for us, we have to recognize what's the order they gave us. So the next question is on your notes, scale factor depends upon the order of comparison. So if we say ABC is similar to XYZ, we could say ABC to XYZ scale factor is 6 to 3 because that compares the two corresponding sides in the order of these two triangles. 6 over 3 is 2. Or we could flip it. We could say XYZ to ABC, that becomes then 3 to 6, and it becomes 1 over 2. So for this section, you have to pay attention to the order they gave you, and if they didn't give you an order, you have to give one. So you have to give this, your order you've given. So here's our next problem. It asks us to determine whether the two triangles shown are similar, and if so, write the similarity statement and scale factor. Explain your reasoning. Now there's a lot to this problem, so I'm just going to kind of give you that brief overview because I think otherwise this is what took so long in the last video. So either way, the first thing is in order to show that two things are similar, you have to show angle pairs are congruent. Well, we're lucky there. We already have two pairs of angles congruent, so I'm good there. But the problem is I'm missing the third pair. If you remember, we don't have to worry about the third pair because we had the third angles theorem. That's what told us if two angles are, if we had two congruent pairs of angles and triangles, the third pair is automatically congruent. So pairs of angles are taken care of. The real trick for this one's going to be the sides and showing that the sides are proportional. So what you're going to have to do then, and I'm going to mark with the markers here just to kind of give you a better visual clue, is you have to match up the sides. So N and Q is between the single and double mark, so is R and S. So NQ and RS correspond. Also, NP is between the single mark and the one I made, and so is RT. So those guys correspond. And then last but not least, leftover sides that haven't been marked yet. That would go between the double and the one I made. So what I need to show is this. Are all three pairs of those sides proportional? Do they all have the same ratio? And that becomes the real work of the problem is simplifying that. So we have NQ to RS, well that's 12.5 to 10. Now, looking at this, it doesn't divide out nicely, but we are just checking to see if this works, but they do want the scale factor as well, so I'll have to give that. So I do need to make sure I get this into a fraction, not a decimal. The easiest way to do this is really just to double both of these, or you can multiply them by 10, and that gives you 125 over 100. That reduces then to 5 over 4. Okay, so I better have 5 over 4 for all of these. So now I did 12.5 to 10. Now I'm going to do 11.5 to 9.2. So again, this is a weird decimal, 11.5 and 9.2. So if I multiply them both by 10, it becomes 115 over 92. And then I have to reduce that. And I'm just going to save you some time and energy here. You can divide both of these down. They're both divisible by 23 actually. And when you do that, you get 5 over 4. So far we're matching up. So our last is to compare the blue ones, the 15 to the 12, which that one actually is really easy to do. Both those divide by 3, 5 to 4. So they are similar. All pairs of sides are proportional. All pairs of corresponding angles are congruent. So yes, they're similar. That's the reasoning we would write out. And then our similarity statement. Now we did 12.5 to 10 and 11.5 to 9.2 and 15 to 12. So I need to do this triangle to this triangle. So I'm going to just say NQP. And then N corresponds to angle R. Q corresponds to angle S. P corresponds to angle T. That's our similarity statement, and then our scale factor would be 5 to 4 based upon this order. If I'd switched all that order, it'd be 4 to 5. Okay, so that was the big beast of a problem. All right, now the rest of this is one theorem and basically kind of working through some more algebra-based problems. So in a second here, again, you'll have the question pop up to you. We're going to solve for x first, then we're going to solve for y. So if you need to, pause it before you get to that question. Otherwise, it'll pop up and you got the prompts in those notes I gave you. So here we go. So I got to find the value of each variable in this problem. the first thing you need to do is we know they're similar, either mentally or again, if it's on like a test or it's on your paper or something like that, you can kind of mark it yourself. Um, Mark out the parts that line up. JM has the single to double mark, and so does TQ. And in fact, right there, I've got my two sides that correspond that are lengths I know, which means I actually have my scale factor. It's 4 to 2 or 2 to 1 if I simplify it. Then match up the other ones. Single mark to nothing. Single mark to nothing. That's 5. And then the leftover side, just one's left over. So really, before you can even do this problem, you have to either be able to do that mentally or have some sort of way to do it. And again, I can cheat using highlighters right now to kind of give myself a visual cue. But what I'm going to do to solve for x is I'm going to have to use the x side. Oops, that's not the x side. Here's the x side. 6x minus 3 and 3. Those two guys correspond. So 6x minus 3 corresponds to, well, some other ratio between the two triangles. And I could try to use the 3y minus 2 and the 5, but that would give me two variables. I don't want to do that. What I'm going to want to use is the two that I know their actual values for both, which are the 4 and the 2. So since I put 6x minus 3 on top, I have to put 4 on top next. And then I have to put 2 on bottom since I put 3 on bottom. Those two guys correspond. And now we're just off to the races solving a proportion. So cross multiply. So 2 times 6x minus 3 equals 3 times 4. That gives me 12x minus 6 equals 12. Add 6. 12x equals 18. Divide by 12. X is 3 over 2, which is 1.5. Or 1.5. Okay. So there we go. X is 1.5. Okay, now our next job will be to solve for y, so we'll come back and do that in a second. So yeah, now I'm going to have to do the same thing, solving for y. Okay. So now this time to solve for y, same exact idea, but I'll use the 4 and 2 again, but now I'll do the 3y minus 2 and the 5. So 3y minus 2 over 5 equals 4 over 2. And some of you might be wondering, hey, can I just reduce the 4 over 2? You can. You know, it does make it a little easier. You cannot reduce across, but you can reduce within. So you couldn't reduce if like 5 and 2 reduced, you couldn't do that because they're on separate sides of the equal sign. And now just cross multiply. So 1 times 3y minus 2, well, that just means 3y minus 2. It actually kind of makes that a little easier. Now 5 times 2. 3y minus 2 equals 10. Add 2. Divide by 3. Y is 4. Okay, so again, hopefully you got both those right. And you just wanted to watch the video. Otherwise, you know, yeah. Last one then here is just a theorem. Okay, last part's just the last theorem. And basically what this is stating to us is, hey, if you've got two similar polygons, you'll know a scale factor. You will. There'll be a scale factor between AB to JK, BC to KL, DC to ML, AD to JM. There will also be, though, a scale factor between the perimeters. And it's the same as the scale factor between the sides. So it says, you know, so you're supposed to copy this. So if you need to pause it or if you just wanted to copy it ahead of time from your book, if two polygons are similar, then their perimeters are proportional to the scale factor between them. Now, here's just a little quick video to kind of, or a little quick, you know, side thing to kind of work that out for you. I've got, let's say, two squares. 3, 3, 3, 3. Perimeter of that is 12. That's the perimeter. Add up all four sides, you get 12. Let's do another square. This is 5, 5, 5, 5. This perimeter would be 20. And all squares are inherently proportional because all their side pairs are congruent. So we know all four sides are congruent, all four angles are congruent. So all squares are naturally proportional to each other. And so the ratio of sides is 3 to 5. And if I do the ratio of the perimeters, 12 to 20, we also get 3 to 5. So that's all the theorem is saying. Hey, if you know the side length ratio, you also know the perimeter ratio. Okay, so good. I was able to cut off a little bit of time for this video. Hopefully it didn't take you too long. And yeah, we'll go over more tomorrow in class.